We're going to continue with section 4.8, but this time we're going to focus on error propagation, which theoretically is analogous to linear approximation, but we use it to approximate a difference rather than to approximate an exact value. So let's look at an example, a motivating example. Pause the video and read example 1. So you see in this case, we're interested in approximating the error of the volume, right? Given that we have a small radius in the measurement of a small error in the measurement of the radius, how much is that going to affect the measurement of the volume? Well, you could just say, okay, look, we know the equation of volume is this, and so V of 9.03 minus V of 9 equals blah, 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 right? But it turns out we can just very quickly approximate this. We can very quickly approximate this difference. So I'm going to take a little bit of time deriving it, but the actual approximation is just very, very quick, right? So normally what we would be doing is we would say, okay, label the error as delta x. I'll call it actually delta r. Maybe I'll just correct that to delta r since we're talking about that. And we're really trying to find this, okay? We want to approximate this. Actually, let me use blue for this. Okay? That's what we're trying to approximate. So here's how we do it. Instead of saying that f of x approximately equals L of x, which approximately equals, this, right? The linearization. We have to remember this function, right? Subtract f of a from, I say both sides, all three sides, right? So that we get f of x minus f of a approximately equals L of x minus f of a, which equals, well, just f prime of a times x minus a. And then we say, well, look, we're really interested in the difference, right? We really don't care about f of x and f of a, L of x and f of a, etc. And we don't even care about x and a, right? So what we're really going to do is we're just going to say, let delta y equal f of x minus f of a. Let dy equal L of x minus f of a. And let delta x or dx, you'll see why we use both in a sec, equal x minus a. Okay? So on the one hand we have, I'm just gonna copy this again. This guy, but this is analogous to saying, right, if we use our better notation here, we're approximating delta y with dy and f prime of a times delta x, or f prime of a dx. Okay? So, for example 1, we use this to say, we use this approach to say, okay, v of r minus v of 9 approximately equals, you could say L of r minus v of 9. I'm not really going to worry about that too much. But anyway, this equals v prime of 9 delta r. Okay? But let's use our differentials notation, right? Because this is just so much nicer. Delta y approximately equals dy, or I should say, sorry, delta, I guess I should call this v, approximately equals dv, which equals v prime of 9 delta r. Okay? And we're going to solve that in a sec. Now, give it a function f. Again, I really call it y. I'm going to call this y. But anyway, this is the difference that we're trying to approximate is the absolute error, or you sometimes see it called the propagated error. Book also uses the word tolerance. That might come up in science. When you take the error, the exact absolute error, and divide it by your so-called nice value, right, your v of 9 in this case, we call that the relative error. And the reason we do this is to put the error in perspective. It's a nice dimensionless measure. For example, you may have heard the measurement that the Earth is 93 million miles away from the sun. But that's not exact. We may be off by like a million or so miles. You say, wait a minute, we're off by a million miles? That's ridiculous. Yeah, but given the measurement of 93 million miles away, being off by 1 million is really just 1/93rd. That's actually a pretty small relative error if you think about it. Okay. So we often multiply the relative error by 100 to get, well, I guess I'll just write the term first. It's percent error. And that's 100 times this guy. And last but not least, f prime of x, delta x is called a differential. Okay, so all we're doing here, what does this derivation boil down to? All we are doing here is the following. We had before that delta v approximately equaled dv, which equaled v prime of 9 delta r. All we're saying here, and really, you know what, I think we could even just call it dr. It looks a little bit nicer. This equals, well, what's v prime of 9? It's going to be, if recall that v of r equals 4/3 pi r cubed, so this is going to be 4/3 pi times 3r squared dr. Or sorry, not dr yet. 4/3 pi r squared, plug in r equals 9, and then multiply it by dr. Okay? And then this is going to give us, it's going to simplify nicely to give us 4 pi r squared, again, plug in 9, dr. And then this simplifies to 4 pi times 9 squared dr. And this, when you just work it out, right, 4 pi times 81, 4 times 80 is 320, so 4 times 81 is 324 pi. And then remember that dr was given to us as 0.03, right? There's our dr. And so this winds up being 9.72 pi micrometers cubed. And that's our answer. So all we did was take the derivative, plug in our nice value, and multiply by dr. Okay? Let's look at another example. Here, we're again given a measurement. We have to find the propagated error and relative and percent error, right, in computing the surface area. Now remember, surface area, I'll call it A, equals, normally for a sphere, it's 4 pi r squared, but it's a hemisphere, so we divide by 2. Okay? Just be a little careful about that. So this is 2 pi r squared. Okay? So all we can say is that, so I'll say 1, the propagated error is approximately a prime of, now let's be a little careful here. What are we actually plugging in? Well, if the diameter equals 2 times the radius, and that's 26, then r equals 13, okay? So we're talking about a prime of 13, which equals 4 pi r, and then we're plugging in r equals 13. Right, and then we're going to multiply this by the error. So actually, maybe I should leave a little bit of this guy. It's just going to be a prime of 13 times 0.5, right? You see I'm getting 0.5 from this guy right here? So it's going to be this guy times 0.5. And anyway, we're going to get 52 pi times 0.5, which is 26 pi. And then this is going to be centimeters squared. Okay. So all we did was we took the derivative, and then we just multiplied it by the error. Okay. All right, so this is the propagated error. The relative error is going to be 26 pi divided by I guess I should say, rather, the relative error is approximately 26 pi divided by, I guess what we could just say is it's a of 13, right? Which is going to be 26 pi times, what was a of, so it's 2 pi times 13 squared, and this is 26 pi. I think this works out to be 338 pi. Actually, maybe I shouldn't even keep it like that. Here, watch. Let me just show you a little bit of nice little trickery here, right? This is 13 times 2 pi. This is going to be 2 pi times 13 squared. Oh, squared? Look at this little trickery right here, right? Cancel out the 2 pi. Cancel out one of the 13s, and we are left with 1/13. Right? And so the percent error is approximately 100 over 13%. Which, no, is not the nicest number. 13 goes into 100 almost 8 times, like 7-ish times, right? You can work that out with a calculator, okay? But that's how you do that. Let's take a look at one more example. Right, let's estimate the relative error of the area of this petri dish, square petri dish. I thought they were usually circle, but here we've got a square. Okay, so anyway, we're gonna say our side length, I guess we'll call it A, equals 10. That's our nice number, and we have that the area of a square is going to be S squared. Right, so you could say, okay, great, A of 10 is going to equal 10 squared. Well, you know what? I'll save A of 10 for a bit later. We won't need that until we do the relative error. So I'll just say A prime of 10 equals 2S, and then we plug in S equals 10, and that gives us 20. And so dA equals 20 times, what did they say the error was? 0.03. And this just winds up being 0.6 centimeters. I guess I should say centimeters squared. Okay. Right, is that? Yeah. Right, yeah, I got that right, okay. So we get that. So the relative error is 0.6 divided by A of 10, which is 0.6 divided by 100. which is 0.006. Okay. So if you're off by 0.03 centimeters, then the area is off by 0.006 or 0.6%. And note that in this case, this measure is dimensionless. There are no units.